guys hear me fine, or? Yep. All right. So today I wanted to talk about implementing blind TCPIP hijacking based on a paper from Frac64. The paper was called Blind TCPIP Hijacking Still Alive. Has anyone read this paper? Or yes, no? Okay, a couple of people, not many. All right, I'll go over it. So yeah, I'm not nearly as badass as the actual paper. However, it's really interesting and seems to have gotten very little attention. I've been trying to implement the paper, however, time constraints and uni has sort of killed all my time, and so I don't actually have a working implementation to release yet. I'll talk about when I hope to a bit later. So I'll just do a run through of the relevant parts of TCPIP for anyone who's a bit rusty. I'll have a run through of the paper, show what kind of issues there are I encounter when actually trying to implement it, how these issues were solved and in some cases still not solved, what can we do with this specific attack, how can we stop the attack, and where this is going to go from here. So I'm mostly a web app guy, networks are not really my thing, but I've been able to sort of model my way through writing parts of this attack tool, and hopefully I'll be able to tell you guys something interesting about it. So I'm also an associate consultant at StratSec in more or less my spare time, since I'm mostly a uni student. This device on the slide is more or less just taken over my life. So if anyone wants to talk about like building operating systems on top of the OKL4 microkernel for this hardware, I am so your man. But that's pretty much everything that's been happening in my life for the past like 10 weeks. However, so to start with the very, very basics, TCP/IP is kind of this layered model. We send data encapsulated inside of like TCP packets, which is encapsulated inside of IP packets, which are encapsulated in Ethernet frames or whatever your access medium is. The attacks we're going to talk about here apply specifically to TCP and IP together. So TCP on some other kind of internet protocol, I'm not sure what it'd be, but like X25 or something, this wouldn't apply there. This is just TCP on IP-based networks. So what IP provides is if you put an IP packet out inside like an Ethernet frame onto an IP network, and you send it to some host, the IP layer should provide some kind of packet delivery from one host to another. The packets look sort of like this. Essentially, three important parts of this packet for this talk is essentially source and destination address, which everyone should be familiar with, but also this 16-bit identification field. I'll explain why in a moment. But yeah, essentially in IP routing, we put this packet out into the network. We say it came from a certain address, and we say we want it to go from a certain address. So essentially, we can spoof these packets, and a receiving host has no way to figure out if that packet came from the host that it says it came from. Again, should be common knowledge, but just want to reiterate. An interesting thing to note is that IP is just best effort packet delivery. It provides no concept of connections. It might lose packets, it might reorder them, which sort of explains some of the design choices that have had to be made in TCP. So this identification packet that I pointed out in the IP header is used, as far as I can tell, to allow for IP fragmentation. If you have different link mediums and different maximum transmission units, or how much data you can put into a single frame on that physical medium. What's this doing? Sorry. If you have different amounts, oh no. Okay. Sorry. If you have different amounts of data you can put onto different mediums, and say you're a router, you get an IP packet off one medium which can send really large packets, and you have to send it out on some medium where you can't. You need some way of being able to split that one packet into multiple packets and then have the host on the other end be able to reassemble them. So each packet that a host sends out is meant to have a unique IP ID, this identification field, so that when a router sort of fragments this into various IP packets, the host on the other end can see, oh, these fragments that I got all correspond to one packet, and puts them back together. So the fact that this paper exploited was the fact that on some operating systems, in particular Windows, this field is incremental. So every time Windows sends out a new IP packet, it just increments the global IP ID counter, and so on and so forth. So in most cases, since like the maximum transmission on most networks is fairly high for what we're going to do, one IP datagram is pretty much equivalent to one IP packet. It obviously can be different, but largely isn't. There are some operating systems where this number isn't simply incremented, but there's some kind of pseudo-random number generator. There has been analysis of these that found that they were weak. However, I'm not going to specifically look at this case, but it can be worked with if you can predict like values a couple of, say, 1,000 into the future. So the relevant parts of the TCP packets we need to look at are obviously the source and destination port, which specify a connection, and these sequence and acknowledgement numbers. So when we have some kind of TCP connection, what we really mean is we have like this, we're sending packets from one IP to another, from one source port on the source IP to the destination port on the destination IP. And this sort of full value tuple specifies the connection. In addition to this, we have these sequence and acknowledgement numbers, which are mostly used to just achieve reliable data transmission, but essentially provide the only real security in TCP. The reason for this is when you send a packet to that for a value tuple of IPs and ports, when a host gets a packet on what is that connection, it validates the sequence and acknowledgement fields to see if it's expecting these particular bytes of the stream at this time. So when you bootstrap a connection, when you do like the TCP three-way handshake, you essentially transfer a sequence number to the other host and you get one back. And every time you send a byte, it essentially has a sequence number attached to that byte. Some flags do as well, but it's largely irrelevant here. So we number each of these bytes, and when we send a packet, we send the sequence number as the value of the first byte in our packet. The ACK number we send is the value of the, is meant to be the last packet we got from the other guy. When this is validated on the other end, it's done in implementation-specific ways, but essentially it's meant to say, this is the last packet we got. Everything before that, don't worry, we have that all. Another thing from the TCP header that we need to note is the window size. TCP controls the amount of data clients are meant to be able to put onto the wire at any one time without receiving acknowledgement of them. This is obviously variable for different hosts and networks and things, but during essentially the sort of startup periods of connections, these windows are kind of negotiated. So that, say, on Windows by default, it'll accept up to like 64K of data without it needing to be sort of acknowledged. So after we sort of say, if we're conducting this kind of attack where we want to inject data into some kind of TCP connection, that's the IPs and ports, and one of the hosts gets a packet. To check if it's valid, the checks it does is, well, first it checks that the packet isn't malformed and similar things, but it checks that the sequence number is greater than or equal to the next byte we expect and is less than the sequence number plus the window size. So we'll accept any sort of byte in the stream within that window size. This is necessary because, again, IP can drop packets, IP can reorder packets. Implementations also sometimes check the ACK value. Essentially, the check that should be done here is that, is this something we have sent? And this isn't something that that's lower than what they've acknowledged. It should really just be, is this something we have sent before? However, we'll see how this actually pans out. But before we go on, so what is this blind TCP hijacking that I want to talk about? Essentially, we want to be able to inject data into arbitrary TCP connections that we cannot sniff. So they're going across the internet in some place where we haven't compromised a box, but we still want to inject into that connection to, say, compromise a telnet session or similar. So the things we need for this largely are the IP addresses for both machines, the server port where they're connecting to. This is largely predictable if your telnet's probably going to be on port 23, and even if you don't know this, you can sort of usually port scan the sort of server to figure out what port the client's going to be connecting to, and this port is usually fairly static. The things we really sort of need to determine in some kind of attack tool would be the client port, the port the client's connecting to on the server. These are generated in different ways on different operating systems, and the sequence and acknowledgement numbers that are tied to these connections. So, some history of how these things sort of evolved from what I can tell. The sort of earliest attacks were when TCP implementations either always started with some specific sequence number, or had some trivially predictable sequence number, or had like some system-wide sort of starting value. And you didn't need to really know much other than the IPs and ports, because the sequence numbers you could guess in a very small amount of packets and just inject data into TCP connections. This was sort of fixed, and we got like pseudo-random number generators to generate our sequence numbers for us, which sort of seemed to be the way to go, but there was some analysis done of them which showed that these pseudo-random number generators were often actually predictable by Michael Zalewski. I also recently found out that he talked about an attack where if IP fragmented a TCP packet, you could essentially you could send another IP packet. If you could guess the correct ID that some IP network had fragmented, then you could get your arbitrary data sort of appended to a TCP packet with an already valid header. However, I'm not going to really talk about that one, since kind of predicting where things are going to fragment and actually make it happen is kind of a corner case, I'd say, that requires special network layouts, which we can't really just engineer ourselves. There's also been some denial of service only attacks. The two that I could think of were if you sent ICMP unreachable packets from the server to the client would go, oh, I can't actually send packets to this host, I should just shut down this connection, without actually validating whether it matched what it was expecting there. And also this attack, Slipping in the Window by Paul Watson, which we're essentially building on here, where he noted that when you're sending a packet, you only need something within that window size. So instead of needing to guess one sequence number out of like 2 to the 32, you need to guess window size sequence numbers out of 2 to the 32, which ends up being, say on Windows where you have like 64K window sizes fairly typically, it just ends up being 65,000 packets, and you can denial of service any TCP connection. There was also a very lengthy survey paper by like CPNI, which is like Center for Protection of National Infrastructure in the UK, where they talked about a lot of attacks on TCP that had been covered before. However, most of this was denial of service attacks and things. It's like 130 pages of text if you want to read it, but it's not all that fascinating mostly. So the actual attack that the article talked about. If we know of a connection where a client is vulnerable or has these incremental or predictable IP IDs, we can send specially crafted packets to the client or server to get the client to send a packet in one situation when our guess was right or wrong, and not send a packet in the other situation where our guess was wrong or right. And by just checking the IP ID of the client by sort of sending like some kind of packet there and getting a probe back, just like a TCP SYN and getting a SYN-ACK or something, we could determine if the client sent a packet in there, and therefore determine whether we say guess the client, the source port right, or we didn't. So who are we going to focus on in this thing, just to sort of give us concrete examples? I keep bringing up Windows because Windows is the client that the paper focused on, and is really easy to attack, more so than any other sort of OS or device I've been able to find. It also notes NetBSD as vulnerable, but I haven't really looked into that. I did poke around on the internet a little, and found this Juniper JunoOS 9.0R 3.6 router that had incremental IP IDs. These things still seem to be administered with Telnet. Some of them you can Telnet into and say, hey, who's actually on this machine? And then you have the IP of who you want to sort of attack right there. They don't have another requirement, which I'll talk about later, but maybe it'll be possible to attack them anyway. So the first part of the paper talks about determining the source port of a connection. What we want to do, we want to sort of, like I said, generate a scenario where we make a guess, we sample the IP ID of the client, we make a guess, send some packets, then sample again, and by seeing if the IP ID changes or not, we know if we guessed right or wrong. In this case, it's kind of convoluted, so I'll have pictures in a moment. So we spoof a SYN packet to the server, pretending to be coming to the client. We set the destination port to the one we think the client's going to be connected to. And we set the port, the client port, to what we want to sort of check if that's the one they're on. If we guess the client port correctly, the server sends back an ACK packet saying, okay, sweet, if we guess it correctly, the server sees the packet, sees it's already part of a connection, but sees that the sequence numbers are wrong. And it says, sorry, no, this isn't what you want to send. You wanted to send with these sequence numbers. So a client which actually gets this back can sort of resynchronize itself. However, if we guess wrong and we got the client source port incorrect, then the server treats this as the client wants to start a new connection from a different source port and sends back this SYN-ACK packet, to which the client will respond with an RST packet because it doesn't know about it. So so if we guess right, the client sends nothing. If we guess wrong, the client sends a packet. In pictures, if we have like our client talking to some IRC server or something, and we're the attacker on the other side of the internet and we can't see what's going on there, but we'd really like to put stuff in there to that tube, we send the TCP packet into like the cloud, and it goes to the server. The server thinks it came from the client. I didn't bother listing the IP up there because we'll just assume the IPs are for the client and server for the moment. But we send this SYN packet to say essentially like start a connection, please. The server responds, sure, we can do that because the source port which we set is 1234 isn't the port that the client already has a connection on. So server replies back, okay, we'll start this connection. But when the client gets that packet, it'll say, I don't know where that came from, like I didn't start that connection. And it'll send a packet back to the server saying, sorry, please reset that connection. I didn't actually do that. In the other case, as I explained before, if we sort of send it onto this IP port channel, the server will think it came from onto that particular channel, but it'll say the sequence numbers are wrong. So it'll reply with an acknowledgement. This is relevant because when the client gets this acknowledgement, it won't send anything back, because if it did, you just result in this ACK storm which just flooded all our networks. So when a client gets this valid ACK packet, it just drops it. Because it already knows the sequence number, it doesn't really help it at all. Are people kind of following this? This one's kind of a bit harder than the others. Yeah? Okay, I don't see any huge head shaking, so try to go on. Okay, my fonts are screwed, but all right. So if you remember how I sort of emphasized that when we send a packet, for this case, we're going to assume it's just a normal ACK packet that the server will drop if it's correct. The server will check that the sequence number is within the expected window. But so to determine more about the ACK checking, one of the things I think I removed from earlier slides was this paper says that on Windows at least that this ACK checking is sort of circular. I have found this to be the case, in other cases haven't. Essentially the idea is that rather than having these two comparisons to see whether it's greater than the initial sequence number we sent and like the last sequence number, there's this sort of sign comparison that due to the magic of C typecasting makes this sort of check sort of circular. So I have a diagram here if I can get a mouse up. So if we have some kind of ACK that's the correct ACK to send to the server, what happens is if we send some like ACK here that's sort of assumed to be correct, that's within that proper like ACK window of stuff we sent, then when that acknowledgement number is subtracted from the our ACK field, it becomes less than 0. And it sort of happens that when you sort of map this on like the circle, like the numbers that this expression here can be, you sort of get this line right across like the number space, showing that like half of them are good values, the other half aren't. So if you pick any two numbers that are 2 to the 31 apart, they're going to be correct because they're going to be on opposite sides of kind of this circle of numbers. So we use a very similar idea to part 1. We send ACK packets, which are meant to be dropped if they're valid, to the client this time instead of the server. We don't have this nasty reflection to deal with. If the sequence number is valid, then since we sent two packets with the ACKs 2 to the 31 apart, one of those packets will be correct, one of those packets will be incorrect. So if we guess the sequence number right, the client should send one packet back to the server. If it's invalid, it should send 2 because because even though one of the ACKs is correct, the sequence number is wrong on both of them. So essentially we detect this difference between 1 and 2 packets being sent. So yeah, as I mentioned before, window sizes are pretty big. They're usually around like 64K. Sometimes they can be considerably bigger with scaled window sizes and things, but they can be as low as 4K. It really depends on the kind of network and devices you have that are communicating. But since we're mostly talking about Windows here, 64K is a pretty reasonable assumption, which means that we only have to probe like 2 to the 32 divided by 64K is also 64K. So we only have to probe like 64K. We only have to send 64K sequence numbers, so twice that. It's not a whole lot of packets. It's a large amount, but it's feasible if you have these kind of long-lived connections. I'll talk about the specific things we could try to target a bit later. But yeah, so essentially this gives us a way to sort of determine what the appropriate sequence number is to send to the client by sending lots of these probes. The third part of the paper talked about how you get the acknowledgement number, because while the sequence number of stuff you're sending to the client lets you inject data into the connection coming from the server to the client, that's usually less interesting than being able to inject data to the server coming from the client, because the clients that you usually want to target are maybe stuff like Telnet, where the user's an administrator, or like, I don't know, an IRC server where you want to be like king of Fnet for a day. But to sort of figure out the exact numbers, we can't use the same technique against the server because the server doesn't have incremental IP IDs. So the idea is we abuse this sort of circular check to do a binary search for the proper acknowledgement number. So if I can get this working, I'll get like a pen or something. So what we try to do is we pick really any number in the space and sort of probe to see if it's valid by using the same like IP ID checking technique. We check if like the ACK here is valid. The ACK, let's see, but we check like if the ACK there is valid. The ACK there isn't valid. We're sort of in this red side. If we do that, we know that the ACK on the other side, like 2 to 31 away, is going to be valid. So this one here is valid. And we know sort of like this line of where the ACK is between those two. So we keep doing this kind of thing, and we probe right between the two closest, like sort of green and red points on the circle that we sort of draw when we program. So we test, like, say there, that's also invalid. So, and we have like a green one over here that I'm not going to bother draw since it takes too long. But essentially we need to now probe right between these two packets. So halfway between there would be there, and it'll be a valid one. So once we know there, we now know that like this ACK is between these 2 points that you can't really see all that well. Where's my mouse? Oh man. So yeah, between this green point and this red point, we know that that's where the ACK is, either there or on this other side. But once we keep sampling enough, sort of sampling right between the 2 closest points, we'll eventually get it down to like this one value that's right. And we know that that's the appropriate ACK to send. So, wow, my fonts are really broken. The problems that you sort of encounter with trying to run this in the wild, the biggest would be that your clients that you'd want to target are mostly behind NAT. So actually being able to probe them for IP IDs isn't the most trivial thing in the world. You can't just send them packets and they'll respond. I'll talk about possible ways to get into this later, but some other things that, like I said, some of the routers I found, like the Juno OS one, have predictable IP IDs. They have huge scaled windows, but they don't have this circular ACK checking. They have a much better case where like they check like the last, like the ACK that you're meant to send minus the like minus 5,000 is about like the lowest you can actually send. So this makes actually searching it much harder and actually finding out what valid ACKs are very tricky. But yeah, there are many different many scenarios that aren't really covered here. The clients behind that scenario, with some really trivial social engineering, you can get around this. Like my colleague Paul did a talk about how you can get like PDFs to persist until like the user essentially shuts down their machine or like kills the process in Task Manager. If you get the user to open up one of these PDFs, you can keep this TCP channel where you can probe for IP IDs alive for hours on end while you run this attack. And yeah, any situation though where you can send a packet to a host and get it to respond is enough to probe for the IP IDs and theoretically conduct this attack. The problem I found actually trying to implement this thing on Linux was that there's no actually easy way to get access to the sequence of acknowledged numbers you're meant to send for a connection. So just the nasty hack is you can sort of just send a packet to yourself pretending to be the other guy, and you'll spit out the numbers and you can sort of sniff them off the network. The case with routers, yes. Most Cisco gears has all their IP IDs set to just 0. Juno OS again seems to have incremental IP IDs. Yeah, if anyone has access to this kind of hardware and would like to give me access to it so I can play with it, it would be very helpful, since I think either my home router or ISP is meddling with my stuff, since testing on the local network is giving me different results to testing over the internet. But yeah, that legitimate access would be great. So the overall problems with this kind of attack, well, it's not listed here, but we actually have traffic going on these hosts. These hosts aren't completely idle. These sequence and ACK numbers and IP IDs aren't just static. We can't just conduct this attack in a vacuum. All these parts also rely on detecting packets not sent. So if there's some kind of traffic spike, we all of a sudden get false negatives, which are kind of a bit worse than false positives, because we have to either sort of detect that we had a false negative somehow, or scan the whole space again, which is bad, obviously. And the first part, where you're trying to find the client port, it relies on reflection, which is really a pain in the ass because you need to also you need to get the timing right. You're not sending all your packets to the one host. Like, even though IP doesn't guarantee no reordering, most of the time your packets do kind of get there in order. But when you're not sending them to the same host, you need to sort of figure out the timing it takes to get for the packets to get from you to the server to the client, and the client to send one out, so that you can do your IP ID probes properly. And of course, they rely on a reachable port. So the problem specific to the first part of client port scanning, we're sending them to two separate destinations. The timing issues are just a pain in the ass, and they found ways to not actually have to deal with it. We're also looking for the host to not send a packet, and again, false negatives. False positives are usually much easier to deal with. You just check it again, and usually spikes are spikes, so they're like errant behavior that after a while just go away. The best solution I found is to just choose better packets. Don't rely on these tricky reflection things. On Windows, if you have Windows Firewall enabled, Windows will first check whether the IP port combination is valid. If it is, it'll let it through to sort of like the native TCP stack. If it's not, it'll just drop it. So if you send something that's going to be an invalid packet that's going to generate like an RST or something, so for example a SYNAC, then if you get the client port right, Windows will generate a packet because your essentially the TCP paths were wrong. But if you don't get the client, if you don't get the client port right, the Windows firewall will just drop it. So you can greatly simplify the attack there. Sadly, this doesn't mean all that much, since the actual port space is so small on Windows in particular that doing a really naive implementation and just going like sleep for a second after like you do each check doesn't make it all that slow. Like, it still runs in 10 minutes. But these solutions, this kind of sort of leads into the solutions that we'll need to other problems. So yeah, again, devices behind NAT exhibit pretty much the same properties. NAT checks like IP and port, but doesn't check sequence numbers. So again, JuneOS, I've been told it's based on NetBSD. I'm not really sure, but so most Unix systems and Linux systems implement this protection against wraparound sequence numbers, which is essentially an option that's meant for high-capacity networks. So obviously, it will be enabled on routers and things, but also enabled on endpoints. The idea is that if you're sending so much data that your sequence numbers wrap around quickly, you need some way to distinguish whether old errant packets should be discarded or not. They do this by having this TCP timestamp option, which they check. For us, this means that if we send like an ACK packet with the TCP timestamp option, this pause check is done before the sequence. It's done before the sequence and acknowledgement number check, but after the port number check. So we send a packet to, in this case, this would be the server, but we send a packet to the vulnerable host with the ports we're guessing and the IPs, and the TCP timestamp option with the timestamp set to 0. If the ports we guessed are incorrect, we get a packet back. If we guess them correct, the host will just drop this packet because of the TCP timestamp option and pause. Again, this lets us work without the nasty reflection issues, but it doesn't get rid of the fact that we're sort of doing negative scanning again. So the solution that I'm going to continue pursuing here is just try to find better packets. TCP implementations are really quite complex things. They have support for heaps of different options. They interact with many different protocols. They have fast paths for special cases. There's going to be lots of different ways that we can actually perform these kind of checks. So essentially, it's just looking for different error conditions in different places and trying to make them essentially leak the information you want. Again, don't scan entire ranges when you're actually implementing this. Like, previously, you had these 3,750 ports. It's much smaller than the whole 64K port range. And also note that Windows Arcade supports sequentially. There's a lot of these implementation details which kind of let you avoid whole stages of things. So the biggest problems really though were with parts 2 and 3. On Windows, ACK checking didn't really seem to be similar. I saw different results against different Windows boxes. Against my box, I saw that if I got the ACK exactly as what it was meant to be, I saw this circular sort of ACK checking condition. But if I didn't, the ACK checking just wasn't done at all. Scanning against like other Windows Windows computers on my network, I didn't see the circular ACK checking at all. So this seems really kind of just dodgy and unreliable. I'm not sure why my computer is different. It might be that it was scanning from within VMware, or it might be a specific fast path. I'm not quite sure. But essentially, over the network, this circular ACK checking doesn't exist. On one hand, this makes it easier. We don't need to send 2 ACK packets for every sequence number we're testing. So if we're only looking to inject data to sort of the vulnerable machine with sequential IP IDs, this means we send twice, like half the packets that we would have to if the ACK checking was circular. However, if we want to send data from sort of the vulnerable host to the other part of the connection, this presents a serious problem because we have no way of determining what the sequence number to that other host is. I currently have no solution to that. I'm still just looking for better packets to sort of send to these hosts to provoke different responses. But a huge problem we have here, again, is that we have to deal with traffic hosts, like, as I mentioned before, are static. The IP ID only tells us how many packets were sent. These packets may not in any way be related to our attack. No host is ever really completely idle. I sort of did this against idle hosts, and I saw they were still sending like 20, 30 packets a second, and even when they were idle, not really doing all that much. This really means we have to sort of have some kind of more sophisticated algorithms, just sort of like check, okay, how many IP ID packets were there. The easiest way to really get around this is like unreliable protocols, just send more packets. So send like 100 packets per port probe. If we see the 100 packets happen, if we see more than 100, we know that it was depending on which packets we're sending invalid or not valid. If we see somewhere like in the 50s, then we know that was probably just like a small traffic spike. If we're dealing with these sort of reflected packets, which might end up being the case if I find nothing to sort of directly determine the sequence numbers to the non-vulnerable host, we may try to do something like send a huge amount of probes for different ports, and then check them on either side, and we just know if there was something valid in that range or not. Again, yeah, that's only really useful if we have sort of reflection issues. We also need to choose how many packets do we send if we do this duplication, because no matter what, this is necessary, but how many we send largely depends on how variable the various connections are, like how big traffic spikes we're going to see. The good thing about when I was sort of looking about how much traffic was sent was with real spikes in traffic, these are usually like from a sort of idle host, like when someone was web browsing to when they like requested a page, you saw like, I don't know, hundreds of % jumps in like the amount of packets you saw in a given period. So these were usually fairly easy to detect, but on hosts that would be, say, like downloading a movie or something, these spikes would obviously be much less notable. Yeah. So another approach we could sort of take with this that has been done in other network tools like the Port Bunny port scanner, if anyone's heard of it. They sort of put these trigger packets within what they're doing. So they were port scanning, but we could essentially do the same thing. If we spam out IP ID probes in between, like when we're actually sending the packets that we expect different responses for, we could sort of get more granular results if we're sending to the same host, because usually they won't be reordered too much. We could do things like detect small spikes and remove them from our total calculations. We could just treat them as lots of different attempts and sort of average the results. I'm still working out, trying to figure out which of these would be a better approach. Yeah, again, these are just the issues. We need to keep looking for better packets to send here, because if we're doing sort of the like negative scanning, we'll end up with false negatives, which are much harder to detect than false positives most of the time. So the interesting thing is we'll be able to do this once it's actually done. So what kind of long-lived connections do we see out on the internet? BGP is probably the most obvious one. However, we already have tools and techniques to essentially denial of service TCP connections, so that's not so much of an issue. But there's still lots of telnet interfaces, so many routers we could potentially figure out where like an admin's connecting to and inject data into a telnet connection, which would be a particularly good target because since we don't, with binary protocols, it's much harder. But if you have a text-based protocol where malformed packets don't get the connection dropped, you just like inject a new line, your command, then another new line, and while what the user was doing sort of gets corrupted, your command still gets executed, and like now have an account on this router. Yeah. Also, TCP interacts and the IP stacks interact with a bunch of different protocols. ICMP in particular, since it's meant to convey error messages and things about what's happening on the network. ICMP has this sort of like next hop redirects that are supported mostly on endpoints, but I've sort of seen some things alluding to the fact that some routers also support this. I haven't really been able to confirm this, but it's feasible that maybe some of the Linux-based routers do actually support them. If we could the things we need to know to sort of spoof ICMP redirects are like the same things we need to know to sort of inject data blindly into a TCP connection. If we have some kind of path of routers across the internet which support ICMP redirects, we could potentially just tell them all, okay, send these packets along this path and have them just come to us, and making this not just a blind attack, but actually being able to see packets. Yeah, maybe looking for other protocols which assume that, hey, if you know all these sequence numbers already, you can probably see the packets, so it doesn't matter if we start sending them to you. Yeah. The simplest mitigation for anyone who cares is simply make sure that the IP IDs aren't sequential so that we can't leak this information from some host. Linux and Cisco routers simply set the IP IDs to all zeros. You may be able to do this with your firewall. Yeah. Yeah, where to from here? So my uni semester ends in 2 weeks, and I get to stop actually developing operating systems, and so I'll hopefully have something out that works by the end of the year. Watch these 2 links. Hopefully it'll all be working and we can like take over FNet. Does anyone have any questions? Also, if anyone is like a network ninja, please come talk to me. I'd love to discuss this and like places where it could go and like get your advice on like where this could be taken. Like I said, I'm not really much of a networks guy. I would love to talk to someone who is. But yeah, if there's no more questions, I think I'm done. Thanks, everyone.